recording. Hello? Hello? Hello, hello. Good afternoon, everyone. You have seen my email and bring up. Yeah, so if you have the lecture summary sheet, please put on the date right away so that you don't forget at the end. You don't have to sign now. And do remember to fill out the midterm feedback form. As a condition to participate in the program, that I would drop the lowest of the 4 exam grades. It's one of the 3 conditions there. Okay, and I plan to return the exam papers today, and so please give me a timeout sign at 2:35. So that's like 10 minutes before the end. Okay, and I'd like to mention a few words. I monitor the feedback response, and so I'd like to mention a few words first. And this is very few students, 1 or 2, but I just want to make sure that everyone is on the same page. The extra lectures are really recommended. These complements my lectures in class, and if you know the material in my lecture notes, it's really up to the individual to decide whether to watch the video. It's really highly recommended. If you look at the lecture notes, you can judge on your own, and we'll get more and more deeper into these aspects. The second point is, in case that my explanation was not clear or is not clear, feel free to ask questions and you get active learning credits. Remember, one of the conditions to participate in the program of dropping the lowest exam score would be to have at least 3 active learning credits. Okay, and I have changed the way I record or take on active learning credits. Essentially anyone who raised their hands, I would pick out, for the active learning credits for each of the critical thinking questions. So feel free to participate. I don't care whether the answer was right or wrong. It's just an opportunity to discuss and participate. Okay. Yeah, and also in case where my response to any question, there have been really very, very few questions from the class. Mostly the questions came from me. So it's hard to say that I did not respond to questions clearly. But in case that I respond to any questions from the class that's not clear, feel free to ask follow-up questions and get active learning credits. Okay. So these are quick points there, and the last point I have already mentioned last time. So you see, it's the background color is magenta, and that will continue on this big picture, very, very big picture. And in fact, the big picture of the first half of the semester has always been there, either through my lectures or in my lecture notes that I will point out later. Okay, I have not had the time to annotate my handwritten notes from last time, but I will do that soon. Okay. Now I'd like to, and again, this is big picture. This is very, very big picture. Dynamic finite element analysis is nothing more useful for an engineer like this topic, right? I have mentioned and motivated regarding the generalized eigenvalue problem. They have seen in this code here. I have provided the my annotated manual, and like I said, if anyone who would like to have the code, I'll be happy to share. For today, I want to focus on fast Fourier transform, FFT, and inverse fast Fourier transform. Earthquake soil structure interaction. These are all important engineering tools. Fast Fourier transform, earthquake soil structure interaction is hugely important, right? And so, to save time, I will use my notes that I already wrote last semester in fall 2014, and so I can move forward. Okay, so here you have seen this. I have rewritten in this class, in this semester, but this was from last semester, so I'm not going to go through this definition of the Galileo. But I'd like to focus on soil structure interaction. You see, this is my annotation, as you know by now, after I had written by hand in class. Okay, so, but I will let you read after class. I just want to zoom into the figure here and present to you this important engineering application. Okay, the idea is as follows. Usually earthquake is a prescribed acceleration or prescribed displacement at the bedrock, right? So this is the soil, below the building. But before you build a building, sometimes you have seismograph that would record the earthquake signals, you know, at the surface of the ground, okay, of the soil layer. But you know, the input is at the bedrock, right? Because you know, earthquake is generated by fractures at the bedrock, and that would propagate up to the surface, right? Going through a soft layer of soil material. This is harder, right? But you know, the signal you obtain is at the top surface. So you want to find out what's the signal at the bedrock, right? Because once you build the building with the foundation of the building on top of the soil, then the signal would be different, right? It's no longer the same as the signal that you measure in the absence of the infrastructure. Okay? So you want to find the original signal at the bedrock, and this signal can be used as input to this model, and then shape the whole system. You know, everything can be modeled by finite element because this is a continuum, and the finite element method is the method of discretizing the continuum, you know, into discrete equation, and that will lead to the equation of motion that you learn in the first half of the semester. Okay, you only learn with two coupled equations, but all of these can lead to thousands or even hundreds of thousands of equations. Okay, so the idea is, you know, the signal here is very complex. It's much more complex than the polynomial that you saw, right? When you took differential equation, you can only, you know, get analytical solution with simple polynomials. You can maybe have trigonometric excitation like sine, cosine, but that's about all. And in this course, you will be able to, you will learn to do something that is more complex than that. But this is really way beyond, you know, anything that you have seen, right? The signal. So, and the tool that would be used would be fast Fourier transform. It's a numerical method tool based on Fourier analysis, and that's the motivation for learning Fourier series and then leading to Fourier transform. But let me, before I go back to that picture, let's move forward with, yeah, so here I just want to show to you, or at least remind you of, you have seen this video already, and I just want to just quickly freshen your mind. Just
This award season, the red carpet has shades of green. The spotlight shines all day. And the best four-wheeler of the year lets you go around.
just keep the air. Just
Dampers. Each 10-ton dampener hangs from a frame. If a tremor causes the tower to lurch one way, the huge hydraulic dampeners swing in the opposite direction, counteract the shift, and prevent the tower from falling over.
Now in these two models, we can compare the effect of fitting a damper. The tower on the left is a normal tower with no damper. The one on the right has a damper fitted to the top. And we can see how much each one sways by observing the arrows at the back. It's clear from this model test that the tower without the damper on the left is swaying more than the tower with the damper on the right.
To test the dampeners in the absence of an earthquake, engineers resort to a novel approach. They carefully choreograph more than 100 workers to sway in perfect harmony to mimic a tremor. During this man-made quake, the dampeners react to keep the tower steady. But on January the 17th, 1995, nature tests the technology for real. A magnitude 7 earthquake devastates Kobe, the city on the Akashi Bridge's north bank. It kills over 6,000 people and destroys more than 100,000 buildings. But the Akashi Bridge survives, saved by its dampness. It still bears the scar of that fateful day. The earthquake opens a fault line in the seabed directly under the bridge. This causes the ground and bridge towers to shift apart and stretches the bridge by over a meter. Engineers must fill this space with extra decking to join it to the shoreline.
As a result of this earthquake, the longest bridge in the world became a little bit longer.
that's all I want to show, and I want you to keep in mind, right, the ground motion, the earthquake ground motion that split the longest suspension bridge by 1 meter and therefore become even longer. And damping, okay, damping, we have addressed damping in the first half of the semester. So let's look at the, and another thing that you want to keep in mind, remember the worker, when they move back and forth, what's that? Periodic loading, right? So we get into Fourier series, periodic functions, and also how do you connect the earthquake signals to periodic functions. Okay. Let's look at the earthquake signals. I have drawn by hand, but if you see the real signal, you would see how complex that is. And so I have here prepared for you this. Okay, so let's let me move this. Yeah, here, good enough. Okay, so first, let's look at, just very quickly, this is a code, Amina, a finite element code. So when you build a dam, you also do dynamic analysis, right? So this is with finite element, and that's, you know, with solving generalized eigenvalue problem to have all the mode shapes. But I'd like to, you can read the details. I'd like to bring to you, you remember listening, watching the video, there was a mention of 6,000 people died in the Kobe earthquake in the mid-90s. Here you have a collection of strong earthquake signals, right? And here in 2011, the big tsunami in Japan, 2011. Let's look at the signal of that earthquake as an example. And here I have, this link here would bring you to the Wikipedia article on the Tohoku, 2011 Tohoku earthquake and tsunami that you can read. And I just want to zoom in into this. This is the ground motion of the earthquake, right? In like Galileo, that's 0.01 meter per second square. That's acceleration. But what you see here is a very complex signal. How do you hope to solve? I'll come to you, Jackie. Excellent. Solve the even the system of second order equations, right? Couple. It could be many equations, but under this excitation, you have no tools up to now to do that. Okay, Jackie, you have a question?
Does that thing list what the biggest earthquake in history was?
Sorry.
Does that thing list what the biggest earthquake in history was?
I think it's rated 9 on the Richter scale. I think, I'm not sure whether it's the biggest, but it's really huge. And it's created a lot of damage. As a nuclear power plant, that is still an issue due to the tsunami. So keep this in mind, and so therefore, an effective tool to deal with this kind of signal is fast Fourier transform. As fast Fourier transform is based on Fourier series as a starting point. Fourier series is like 2 + 2 = 4, and you build up on that, leading to fast Fourier transform. Okay, so that's the motivation. That's big picture, right? Is there any picture that is bigger than this one? That's very difficult to have anything that can motivate the learning of the topic that is in this course. But still, I have something now. So now this is very complex. Okay, this is well beyond the capability of this class. But here is something that is reachable. Okay, and this you have seen. Since the beginning of the course. So let me close a few. I'd like to, just a few words about this. So you see the complex signal. So what you do here is to build a finite element model and solve the inverse problem. Okay, for the inverse problem, this is the input. That's the signal at the surface of the ground. And the output of the inverse problem is the signal at the bedrock. That can be used as input to this model too, with the presence of the building. Okay. There's two problems. There are two types of problem. The forward problem is when you put the signal at the bedrock and find out the output at the surface of the ground. That's the forward problem. For the inverse problem, the input is the signal at the surface of the ground, and the output is the signal at the bedrock. So there are two different types of problem there. And let me close a few tabs there. And section 0B, the big picture. This is lower level big picture, closer to the level of the class studies. And let's look at that big picture. So this is not as big as earthquake, right? The picture, that's what I mean. So section 0B, we look for that right here. Don't tell me you haven't seen this before. This I have shown at the beginning of the course to motivate why we look at the system of coupled linear second order ODEs, right, with constant coefficients. And so, so the applications, right, multiple degrees of freedom system you have seen through vibration, but it also can be used for circuit electrical in electrical engineering. You have seen these tools. We have derived the generalized eigenvalue problem. Look at the concept of orthogonality of the eigenvectors with respect to mass and stiffness, and projection of the displacement or solution on the basis of the eigenvectors, right? So all of these allows you to uncouple the system so that you can solve each equation independently, right? And solving each equation independently, that comes to the scalar linear second order ODEs. Okay, so that's one big picture. The next big picture is going back to the scalar second order ODE. Even in this picture here, you have a lot of application. But there are things that I'm sure you have not seen before, even in differential equations. For example, general excitation. Right? An example of general excitation would be logarithm of 1 plus x, for example. That you don't have any tool to solve, with the knowledge from differential equation. But in this course, you will learn how to do that. And then we'll talk about periodic excitation that you may have seen with sine and cosine. But here we are talking about more general periodic excitation than just sine or cosine functions. Okay? So what are the tools? The tools are, an example would be using Taylor series. How do you connect Taylor series to solution of second order ODEs with constant coefficients? Let's give some opportunity for students to participate here. Again, if you'd like to participate in the program of removing the lowest exam score with constant coefficients, right? And so recall that. Let's say you have this and let's assume, okay, let's take a complex function that you don't know how to deal with. Let's say logarithm of 1 plus t. T here is the independent variable. But the hint was that in the big picture, the hint, like I said, one method is Taylor series, right? Everyone knows how to expand in Taylor series. So with that hint, okay, the hint, Taylor series, and this linear second order ODE that is excited by this complex function logarithm, what would be the conceptual step to solve this problem? Let's assume that you have both the initial conditions, right? So you have, let's say you have y at time 0 equal to y0, and y prime at time 0 equal to v0. So displacement and velocity, modal displacement and modal velocity. Okay. So how would you solve this problem? Let me start with the first step. Okay, expand this into Taylor series. Let's say about t equal to 0. Then what do you get when you expand into Taylor series? When you expand a function into Taylor series, what do you get? Anyone? For active learning credit? Say, for example, if you have r of t, right? Expand about t equal to 0, that will be r at 0 plus dr over dt at time 0. What would be the next term? Anyone? What would be the next term in the Taylor series? Okay, so we have Colton, we have Matt, we have Kevin, team 6. So Kevin, team 6, and then Matt and Colton can add on. Second derivative of R about at time t equals 0. How about a factor? There's a factor. Not just the second derivative, 1/2. Yeah. 1/2 of it. Okay, thank you. How about Matt and Colton? You agree with Kevin? 1/2 of the second derivative of R? Okay. So what would be the general term? So second derivative of R at time 0, right? And let's say if you have plus dot plus, let's say the nth derivative here n. What would be the factor in front of the nth derivative? Matt, anyone else? John? Okay, Matt?
That'd be 1 over n factorial.
1 over n factorial. John agrees. Okay, so 1 over n. So this is also a review for many years. Do all of you agree? Is there anything missing? Of course, when I ask that, there's a hint, right? And I even leave some space here. So think about this, and while I'm noting down contributors, so I see Colton raising his hand already. So this is meeting 31. So I have Colton. Kevin is team 6. While I record down the contributors, please think about what I just asked. So we have Kevin. Is there anything missing in that formula? So Kevin, Matt is team 8. Do I miss anyone else? John, you are team 5, right? Team 4. What is missing over here? Very important. You know, let me give you a hint. So far, what you see here are all numbers, right? I mean, R at time 0 is a number. Derivative of R at time 0 is a number. 1 over 2 times second derivative of R at time t equal to 0 is a number. All of these are numbers. What is this? This is a function. A function cannot just be equal a number. So that means that there is something missing on the right hand side here. What is that is missing? Yes. 1, 2. Yeah, what is your minus a
or like some point in.
like some point a
Like I thought you meant like x minus a or whatever.
x minus a.
Yeah.
Okay, so
X minus a.
yeah, so you think of a as 0 here, right?
Yeah.
Then I say expand about 0, so a equal to 0, and instead of x you want t.
Yeah.
T is time. So what is your name?
Richard.
What t?
3.
What?
3.
Team 3 and Tony team
7.
7. Okay. Very good. So essentially, Richard, Tony, team 7. Okay, so while I do this, you should write in your notes so that see whether you can guess what I'm about to write in here. It should be t here, and this should be t squared, and this should be t to the power n. Okay? What do you have here? Can you now solve the second order differential equation excited by logarithm yet? Can you do that or not? Okay, so let me provide yet more opportunity for active learning credits. Let's go back, okay, and review even this problem here. What is the first step in solving a linear second order ODE with constant coefficients excited by anything? What are the general conceptual steps, Devan?
We want to break it into the homogeneous form and then.
Very good. I forgot to ask more contributors, but next time. Okay, so Devan said decompose into a homogeneous problem and what? Particular problem, right? So decompose solution into or actually instead decompose the problem into the homogeneous problem. Don't worry, there will be more and more opportunities to contribute, okay? And the particular problem. So now here, contribution, how do you write the homogeneous problem and how do you write the particular problem? Okay, so this should be really quick by now, so please, but it's important. Okay, let me make the first step and then you can contribute. So the first step is I copy the left hand side, and so how do you express the homogeneous problem? So Paul and Caleb, right? Okay, so let's see, Devan is team 6. Okay, so Paul, go ahead. How do you express the?
You just set it equal to 0, right? Yeah.
Sorry?
You just set it equal to 0.
Set it equal to 0, Caleb?
Set it equal to 0.
Set it equal to 0. Any other contributor? Is that all you want? Okay, so let me write down what everyone says and see whether you all agree. Is this what you want? Let's let's recall, in math you want to be rigorous, okay? You really need to, so this is the original, yeah, let me copy the whole thing here. Maybe just this is enough. So that you can see side by side. This so this is the original problem, right? And now you want to decompose it to two problems. Is it the most rigorous way to write? Any contributor? Think about this while I note down Paul and Caleb. Paul, what team number?
3.
Team 3. Team 3, okay. Caleb, what team number? 5, okay. Anyone? No one? Here. you cannot write y. You have to write y sub p. Sorry, y sub h. I was thinking about the particular problem already. Okay, because y sub h is not equal to y sub h is not equal to y. The decomposition means that you write y equal to y sub h plus y sub p. Okay? And y sub p is the solution of the particular problem. Okay, so now particular problem. Okay, so now let me write the following. Okay, I think by now everyone knows, so let me move forward and pose the question, more advanced question. Okay, so this would be P, right? So the particular problem has to satisfy the actual excitation. Okay. And now recall that the excitation, the actual excitation, we took the example of log of 1 plus x, for example, 1 plus t. But in general, for any function r, you can expand into Taylor series, right? And the Taylor series can be written as the sum of some coefficients. Let me use c I to times t to the power I, with I going from 0 to n, for example. N can be infinity, right? Let me copy this line down so you can see why I can write like this. Taylor series is a particular case of this series here. What is the name of this series? I have mentioned that at the beginning, in the first half of the semester. This is a power series. Okay, the Taylor series is a particular case of power series. So, given any complex function, you can expand into Taylor series, and Taylor series is a power series. If you excite a linear second order ODE by power series, can you solve this? Can you find the particular solution? You can find a homogeneous solution, right? That's easy. We don't need to go back to that problem anymore. The issue now is a particular problem. So, if you are given all of the coefficients C sub I, you know that, because C sub I are the coefficients of the Taylor series here. That is known. Can you find the particular solution? Do you remember a tool in differential equation that would allow you to find the particular solution? In fact, you should know that, because that's part of exam 1.1, right? 1.1, problem 2. I didn't give it, but it's problem 2. So we have Dylan.
Is it a variation of parameters?
Sorry?
Variation of parameters?
Variation of parameters, be careful. Variation of parameters is really for the homogeneous solution when you have double real root. That's the only time that you need to appeal to variation of parameters. But for linear second order ODE, you know the result. The result is just by taking the first homogeneous solution multiply by t or x, depending on what is the name of the independent variable. But here we are talking about particular solution. And if I show to you the statement, the statement of problem 2 in exam is, I set up the alarm to remind me to stop 10 minutes before the end. But let me complete this story, and then we'll return the exam papers. Okay, so I think it's here. Yeah, right here. You already forgot. This is linear second order ODE excited by just one term. But remember, to find the particular solution, you really have to have a series that starts from t to the power 0. That's 1. T and then t to the power 2. Okay, that is really the main point of this problem here. And then you find the undetermined coefficient. The van, yeah,
So
question.
then it would be the same as taking the left-hand side of our equation and setting it equal to each part of the polynomial.
Okay, very good. The van asked a very excellent question. Here in the case of, and let me just answer this question, and we can return the exam paper. So in this case here, you have the whole series starting with the 0 power to whatever you want to truncate the Taylor series. Because Taylor series is infinite, okay, infinitely many terms. But you need to truncate because you cannot solve infinitely many terms. So the trial solution is similar to this one, but instead of c sub I, you have the unknown coefficient d sub I. So you have from d0 to dn, that's n plus 1 unknown. And you need to come up with n plus 1 equations to solve for these n plus 1 unknowns. Okay. But the example is already given in my lecture notes in section 7, and as well as in my coaching of solving problem 2 of exam 1.1. Don't forget that. Okay, so Michael, maybe you can help to lay out the while Michael helped to put out the exam papers by teams. So I'd like to mention the following to you. We'll return the exam papers by team. So I will call out the team numbers. So please have a pen with you, so that when you pick up your, Michael, you can perhaps you need to sign on the sheet, and do not pick up the exam papers of anyone else. Okay, just only yours, and sign on the sheet to indicate that you already picked up your own exam papers. Yeah. So by team. So maybe yeah, just team 1 to team 9. So we will use on this side here. So team 1, see team 1, you can come and pick up. Have a pen with you so that you can sign on the on this sheet here. And keep the stack, organized so that the next person can pick up yours and sign it. Team 3. Team 5.